strain. So strain is basically an amount of deformation in a material due to applied external load. So the amount of deformation a material experiences, that's called the strain. Remember, there is also one more term that is called displacement. Deformation and displacement, both are different. Deformation is the relative motion of a point with respect to a reference axis. That's called displacement. Displacement with respect to a fixed reference axis or origin. That's called displacement. Deformation is basically relative displacement between the particles, between two particles. That constitute deformation. Okay, so strain has both components. It has displacement and it also has deformation. And so let's move. Then something next comes. That's called your linear elastic behavior. Because in all our courses on solid mechanics, we learned something called Hooke's law, and that Hooke's law is based on certain assumptions. What are those assumptions? That our material is elastic, and especially it is linear elastic. What do you mean by linear elastic? Linear elastic means my material's stress strain diagram is linearly proportional to each other. That's your elasticity. Homogeneous means its material density is constant at every point inside the body. It means it is related with mass distribution or density distribution in the body. Third assumption is about isotropic. It means that its material properties are same in every direction of loading. So these are the three assumptions that we go for. So we have something called a small strain assumption. What is the small strain assumption? Because only under the small strain my material is elastic. If I go for a large deflection, as you know, my material will transform from elastic, then it will yield, then it will go to plastic domain. So that is not in our interest, plasticity. We are only dealing with elasticity. So we have something called a small strain assumptions. What does that mean? That means our strain is less than 1%. It means within less than 1%, we have certain assumption. Of course, as you already know from the stress strain diagram, in practice, what is the value of the yield strain? What is the value of yield strain in reality? I think you know the offset rule that we use in the stress strain diagram. It's like 0.2% offset. So you can assume from there that in reality it is less than 0.2, sorry, in reality less than 0.2%, but less than 0.1% is more common. Now comes strain types. We have 4 types: axial, bending, shear, torsional strain. As you know, axial means we are having normal stress and normal strain. It means only its shape not changing, only its size is changing. What happens in bending? The resultant strain is 0, because let's say a body is bending in the downward direction, the upper half is getting elongated, bottom half is getting compressed. So effectively there is no strain. They cancel out each other. That is the definition of your neutral axis, which we get in bending. Then we move to shear. Shear is change in shape of a body, not size, shape. That is your shear strain. And it is related with torsional loading. So whenever we have a torque elements or shafts, they are subjected to torsional loading and they support shear loading. Now, one more: normal strain, shear strain. We have certain difference. Normal strain means its size is changing, but shape does not change. So for example, if I have a rectangle and I elongate it, it will still remain a rectangular in shape, but its length and height, it will change. Shape is still a rectangular shape. Come to shear strain, shape changes, size does not changes. So what happens in this case? let's say I have a rectangle, and when I apply shear load to it, it deforms into a parallelogram. The length of the size is still same, but the shape is now different. Originally, it was inclined at all the edges were at 90 degrees, but now their angle is changed. So that is the difference between shear and normal stress strains. In the Hooke's law, we already know that stress is Young's modulus times strain. Similarly, Hooke's law for shear strain, that shear stress is the shear modulus times shear strain, which is gamma. Next slide is something called piezo resistivity and a strain gauge. Remember, strain gauges, they work on the principle of piezo resistivity. So piezo resistivity means, as the name is suggesting, piezo means pressure and resistivity means resistance. It means electrical resistance. So when we apply pressure to a body, its electrical resistance changes. That's called piezo resistivity. So our strain gauge, they uses this property, that's of piezo resistivity. So it was discovered long back in 1856. Lord Kelvin, he reported this. Then electrical resistance of a conductor of resistivity rho here is given as R is resistance, rho is resistivity, L is length of conductor, and A is cross-sectional area of the conductor. Then from here we get the relationship for gauge factor. It is a parameter that is critical of any strain gauge. So what we do here, we simply take a derivative of this equation. It becomes like this, and then we rearrange it. This term dl by L minus dA by A, we write this term in terms of Poisson's ratio. I think solid mechanics we have already learned about Poisson's ratio. From this term we get something called gauge factor, and it is the ratio of fractional change in resistance per unit strain. Delta R by R, it is the fractional change in resistance per unit strain, and it is given as like this. Remember, dl by L is basically strain here. This is a strain, change in length divided by original length. So here is a strain. So it becomes d rho is resistivity, not density, resistivity, electrical resistivity per unit strain plus 1 bracket 1 plus 2 times Poisson's ratio. So remember this correlation, because I don't find many places this sort of correlation related. It's very important. What is its importance? The importance is that the change in resistance is, let me use the annotation. Yeah. So if you look at here, the change in resistance, it is proportional to electrical property of the material as well as its geometric property, or you can say mechanical property, because Poisson ratio is a mechanical property of a material. So it change in resistance, electrical property as well as mechanical property, or you can say, because length is also involved, you can say geometric property also. Now, strain gauges are many types. We have like metallic strain gauges, we have semiconductor based strain gauges. So different types are there. Here our focus is on metallic one. It means we will not be considering this term. We would only be focusing on this term. Okay, because in metals their electrical resistivity does not change as much compared with their Poisson's ratio effect. So this effect, it dominates in metals, metal strain gauges. This term, first term, it dominates in semiconductor, electrical one. Now here is one more thing. Now another thing, just notice here that gauge factor is equal to here GF is, oh sorry, it is 1 plus 2 mu. Now can you tell me what could be the value of this term for a metal? What could be the maximum value of this term for a metal? Or let's say, what is the value of Poisson's ratio for a metal? Maximum value, how much? For steel, what is the value of Poisson's ratio? This is the point. Three. It means what is the value of this number? 1 point. Okay. 1.66. So what does it mean? That the gauge factor for metals is about 1.66 minimum. Remember, this term will also play some role. You have to add them to. What do I mean to say? That in gauge it is about 2. The gauge factor, our strain gauges. What is the value of gauge factor in there? Their gauge factor is very high. It's more than 50 for semiconductors. It depends on type of semiconductor, but it is more than 50. Why it is so high? Because this term dominates, the electrical term dominates there, and this term is not effective, because as you know, silicon is a brittle material. It cannot undergo large plastic deformation and large Poisson ratio coupling. So it will go. So anyway, to just understand piezoresistivity, metals, semiconductors, their phenomena is different. Now move to our next topic. I hope it is clear to most of you. Then next is about strain gauge. So strain gauge is, as you can see, it has not completed even 100 years. It was invented in 1939. Then what happens in strain gauge? Its electrical resistance varies in proportion to the amount of strain. So as the name is suggesting, electrical resistance is changing because it's a piezoresistive device. Metallic foil strains are most popular type. Metallic foil strain type. Then we have gauge factor. I already explained. Gauge factor is fractional change in resistance per unit strain. That is the definition of gauge factor. Commonly used material in strain gauges are, this is most common use, constant N. What is constant N? It is an alloy of nickel and copper. What is this gauge factor? It is about 2.0. Look at here, I have put a sign of positive. What is why I am saying positive? Can gauge factor also be negative? The answer is yes. Gauge factor can also be negative. So our objective is to go into the positive. If they have the positive values, we will see in the next slide when gauge factors become negative. Another material is isoelastic. Its gauge factor is 3.5. Remember, just we discussed for metals it is about 2. Here I am getting 3.5. It means the electrical resistivity is also playing a significant role. Rho term that we saw last time. Geometry is playing, but geometry cannot play more than 2. It means our electrical resistivity is also playing a role. Then another material, carbon, again it's an alloy, nickel chromium plus addition, gauge factor is about 2.1. So most of the time these strain gauges that we use, they have gauge factor about 2. Next comes, here is one diagram. As you see, the x-axis is showing the percentage change in resistance, and on y-axis you see the increase in length. Length of what? Length of metals. So let's start with the here we have platinum, here we have aluminum, here we have nickel, aluminum, here again, then copper. Remember your limit, strain limit was 1%. Okay, it means 1%, somewhere here is the limit for our strain gauge. So you see, look at their behavior. Let's say aluminum, when we increase its length, we move from here to here, its resistance is increasing, and then it starts to decrease, you see. It means now gauge factor is becoming negative. Gauge factor is positive because resistance is increasing, gauge factor is becoming negative. So that's what the concept. Now come strain gauges. How do strain gauges look like? As you can see, these are all Omega brand. Omega is a very famous brand that makes strain gauges. And then next is about, once we have the resistance, how to measure that resistance. So to measure that resistance, we have something called Wheatstone bridge. What is Wheatstone bridge? Wheatstone is the name of the inventor who developed this bridge. And it was developed in 1843 by Charles Wheatstone. What is its purpose? It measures unknown resistance and impedance. Resistance and impedance. You can say DC resistance is resistance and AC resistance is called impedance. So in DC circuits, we have only resistor. But in AC circuit, we also have capacitor and inductance. So there we have something called impedance. So you can say equivalent. The DC equivalent of resistance is impedance for AC. This is the circuit diagram. How it takes, So what we have to remember here? Remember the polarity and the notation that we are using. We are counting like this in the anti-clockwise. Resistance 1, resistance 2, resistance 3, and resistance 4. This is the order in which my resistances are placed. Look at the excitation. The positive voltage is coming from here, negative is from here. Similarly, our negative voltage is here and our positive voltage is here. Okay, remember this. This is how this circuit is made. So we cannot interchange the things. So based on this circuit, this Wheatstone, you see VO means output voltage is equal to R3 here divided by R3 plus R4. It means your right side, this is the left side. So right side minus left side resistance, R2 divided by R1 multiplied by excitation voltage. O means output, EX for excitation, which we are giving it. So remember the polarity, plus here, minus here, then plus here and minus here. R1 here, R2 here, they are in anti-clockwise order. Then we have this formula for that, change in resistance. Then Wheatstone bridge, there are many arrangements for this. So we start with something called quarter bridge arrangement. Quarter bridge, let's see the diagram. So in quarter bridge, how many resistances I'm using? I'm using only one. Look at the diagram. Here, I'm using only one variable resistance, RG. That's your gauge resistance. This is one active resistance, which is taking part in my deformation. So look at here. What type of loading is this? I think students, they cannot speak.
Sir, actually, they are mute.
Okay, fine. Okay. Then I thought it would be very interactive from both sides. Anyway, so as you can see from here, this is yes, someone has written correctly. It's a tensile loading, correct? So here we
Students
are
can
having a
write in the
tensile.
chat box.
Yes, I have opened chat box, so students you can write your answer there.
Okay.
So here we have a tensile load. On here I have put one strain gauge here. Oh, one more thing which I would like to mention here. Let me show you strain gauge. Where's strain gauge? Here I have a lot of things with me, so I hope not a good contrast. Okay, let me focus the camera on my what I do. Wait just a second, a little more. Okay, wait. Okay, no, it's too. Much. Okay, fine. Let me see what I'm showing. My own. Wait, I have to how to make my own video big, because only then I can see. Okay, so here you can see with me. I hope with me here you can see something in. I
Yes, sir.
think
It's quite
contrast is not
visible.
good. Huh?
It's quite visible.
Okay, it's quite visible. Then it's good. So because actually my window is just I think 1.5 inch is showing me, so I don't. So here with me I have this a strain gauge. It is a red colored, and let me take it out from here. Here you see in my hand. This is a very thin. I mean, you cannot. How thin it is? So very thin, about less than 100 micron. Human here. This is one strain gauge. Now the strain gauge, it can only support, or it can only sense axial loading. What do you mean by axial loading? It means, let's say I put my strain gauge back in its envelope, just to show you just the concept that if this is the direction of a strain gauge is in this direction, horizontal, it can only sense its strain in horizontal direction. Let's say I'm pulling it like this. Okay, I'm pulling it like this. So it can only sense only that strain which is parallel to its axis. Okay, parallel to it. So it can only sense normal strain or elongation. That's all. Elongation or compression. The strain gauge can only sense strain, normal, compression, or tensile load. Okay, it cannot work for the side. If I want to pull it from the sides like this, no, it will sense something, but that will be junk data. It is not designed for this purpose. It is only designed for this purpose along the length of the gauge. Okay, then so this is here. I have one more here with me. Here, if you can see here, I have one steel scale that we normally use in genetic scale. Here I have mounted one strain gauge, red colored, if you can see, and this is its. These are the two wires, output wires. And these wires are used to measure what is the change in resistance. Of course, because I'm using only one resistance, so it is quarter bridge. The question is, where are the other three bridges? Because in Wheatstone, there are always four bridges, four resistances. So I'm having only one. Where are the other three? So those other three are part of the circuit. So we put 120 ohm resistors. This is, yeah, that's important. Why it is 120 ohm? What is 120 ohm? So 120 ohm is its original resistance. Its original resistance is 120 ohm. When I put a strain to it, its value changes. Its strain value increases. If I put it like, if I bend it like this, let's say for example like this, in the downward direction, as you know, because it is on the top surface. So on the top surface, we have bending phenomena, elongation, and at the bottom surface, we have compression. The top surface is elongated, its electrical resistance increases. If I put it like this, and I again bend it in the downward, then its electrical resistance will decrease. It will decrease because its length will become short and its cross-sectional area will increase. So that's how we do. So this I was trying to show you the example of quarter bridge. Here is one example of a quarter bridge circuit, but it is not a good idea. Quarter bridge is not a good idea because my readings are very erroneous. Now, so here we go for what we say. From quarter we move to half. So look at one example. I already showed, right? This was the example that I showed you with my bending example. At the same time, I can also put a tensile load to it, like pulling it apart, and then I can see it is being subjected to a tensile load. If I pull it down, again tensile load, but actually that is the bending phenomena. So in such a case, what is the output? Remember, next question, how do we measure output? How do we give input, excitation? Is it AC or DC? We give DC excitation, DC voltage. How much we give, it depends on what is the resistance of this strain gauge. This strain gauge is not about it, it is 120 ohm. This is industry standard. 120 ohm, 350 ohm, 1000 ohm. These are the industry standard strain gauges. So accordingly, we give them their power supply. So here, if I'm using just one bridge, one gauge, strain only one. In this case, the output voltage, which I determine from here with the help of Wheatstone bridge. I can use a digital multimeter, but remember the change in voltage is very small. It is in millivolts. And like I have multimeter with me here, but you can see multimeter, what is its smallest voltage it can measure? Where is the voltage? DC voltage, of course, it is a DC one. It can measure up to 200 millivolt. It can measure only up to 200 millivolts. But of course, not everyone has a multimeter that can measure in millivolts. So the problem is how to measure this. So that's why we use amplifier and some circuitry is there. So if you have a multimeter which can measure millivolt, very good, go for directly measure it. If you don't have, then you have to go for amplifier and other electric circuits. So this is half bridge, or sorry, not half, quarter. Quarter means only one gauge is active. Only one gauge is active. Others are just dummy. It means standard. I can use 120 ohm standard, the three. Okay. Then next comes, we have one problem. That problem is called temperature effect. Can you tell me why temperature comes into the picture? You may type why temperature is important. Because as you know, resistance is a function of temperature. So original resistance is 120 ohm, maybe because I'm doing an experiment, maybe in Nagpur. Nagpur is very hot place. So what will happen to your resistance? Its resistance is already high. So to eliminate those effects, we put also something called a dummy gauge. It does not take part in your measurement, but it only eliminates the temperature effects. Now, I think the time is still 12, right? The lecture hour is from 11 to 12.
Yes, sir.
Okay, fine. So I would be then moving quick. So half bridge, I think you are also recording it, right? So
Yes,
maybe
sir.
you can share the recording with the studios, the slides.
Yes, sir.
So okay, temperature. So to eliminate temperature effect, we put one dummy also. The dummy does not take part in our supporting any strain. It is only for eliminating temperature effect. Then comes half bridge. What we do in half bridge? Half means two. It means two strain gauges are now active and they are supporting load, something like this. Here we have a tensile loading case or axial loading. One of my, look at the directions. One of my strain gauge is lying, this is its axis, and another axis is here. So this measures directly the strain, and this one measures the again strain, but this is your transverse strain. One is longitudinal times longitudinal. This is directly longitudinal strain, and another is transverse strain. So it is half bridge. Similarly, we can go for bending case. Here, same arrangement, bending load. Again, here it's the positive, here is negative ones. Then now configuration type 2. In this case, let me show the type and then I show. Here what we are doing for bending case, we are putting one at the top. Of course, both are in this direction only. One is at the top surface, one is at the bottom surface. So the top surface, let's say it is bending in the downward direction. It would be under tensile, it would be under compressive, resistance will increase, resistance will decrease. In this case, this is my circuit again. Circuit is same. What would be the output? Output would be like this. Gauge factor into strain into. So because external and this, I already know from my multimeter. This is from my battery. Gauge factor, I know if this the gauge factor is generally 2.1. Multiply, I can find what is the strain. Strain is equal to what? I can calculate it directly. I'm using half bridge. Then we can go to full bridge. This is the most common. We use full bridge most of the time. It has its advantages. What is the first advantage? Look at its sensitivity. What is the formula? Output is simply gauge factor times your strain. Look at the previous one. Gauge factor strain by 2. Look at the quarter one. Gauge factor into strain by 4. So what does it mean? If I'm using quarter, my output is only 1 by 4. If I'm using half bridge here, my output is half. And if I'm using full bridge, my output is full. So in quarter bridge, output by 4, half bridge output by 2, and full bridge pure total output you get here directly. So here we have, in full bridge, we use four gauges, 1, 2, 3, 4. 2 are in tensile mode, it's here. Other 2 are in compression mode. And they all add or contribute to our resistance change. Then we have type 2 configuration. We can also go for like this, bending again in the downward direction, 2 in the axial direction, 2 in the transverse direction. Of course, Poisson ratio coupling will take place, and then we can calculate it. But remember always, your circuit layout should be like this only. The whatever circuit you made, it should be like this: 1, 2, 3, 4. The anti-clockwise order: 1, 2, 3, 4. Okay, so then we have one more, not so important, I think. Okay, here is some. Then one more is here about something called a strain gauge. So it depends on your application. You want axial loading or bending loading. So you can use type 1, type 2, which I have shown previously, or you can half bridge, type 1, type 2, or full bridge. Now something called sensitivity. What is this? 1000 microstrain. What is this 1000 microstrain? Remember, what is the value of a strain? From our let's say offset rule. As a rule of thumb, it is about 0.1, less than 0.1%. The real strain elastic strain or yield strain is less than 0.1%. Now I am going to write it in terms of microstrain. So it would be how much? It is basically 1 millistrain. It is 1 millistrain. 0.1% is 1 millistrain. Or you can write it like 1000 microstrain. Okay, so you can say 0.1% strain, 1 millistrain, or 1000 microstrain. Okay, so don't be confused. It is this. It basically means 0.1% strain. Then what is the sensitivity? It is 0.5 millivolt per volt. What do you mean by that? What do you mean by this value? It means that, let's say my excitation voltage is 10 volt. VEX is equal, VEX is equal to 10 volt. Okay, and my sensitivity is this much. Then what would be the V output? What would be the V output? V output is shown here. So let's say 0.5 millivolt per volt. Because my input is 10, this is input. So multiplied with 10 at the top and 10 at numerator, and 10 at the denominator. So it means if I'm applying 10 voltage of excitation, What would be the value of output voltage, V external? It would be 5 millivolt. Okay, so this is the value of this number, that if I'm giving an input of 10 volt, it will be 5 millivolt will come out as the output for this circuit. Okay, next. Okay, so I already mentioned 120 ohm, those are the resistances, then 350 ohms, 1000 ohms. Most commonly we go for 120 at research levels. In industry, we go for 350 ohms. They have their own advantage, disadvantages. We will not talk about it. And then we have excitation voltage. Why I not give them 100 volt? Why only 10 volts? The reason is current, I square R heating or Joule square heating. Because of the heating, there are many noise in the system. Then I would go, next slide is, here is one. This is the same one that I showed you previously. This is just a data sheet that comes with it. So as you can see, the gauge length is 5 mm. It means between this point and this point, this length is 5 mm. Gauge resistance is 120 plus minus 0.5 ohm, R0, original resistance. What is the gauge factor? 2.13 for this particular model. I also bought some from this, as you can see, this is from Amazon. Amazon, of course, our Amazon only. So it is about it is again 120 ohm resistance is there. And you can see from the back side, if you follow, it is there in a pair of two they have given. Now comes load cell quickly. Here is something load cell. I have with me a load cell also because I do instrumentation. So I know I have all these equipments with me. Here, this is an Arduino, we use for instrumentation for making load cell. This is HX71. It is its amplifier that we use with in combination. Here we have just a simple breadboard for electrical connections. This is a load cell. As I showed here, it is already have full bridge arrangement. It means four strain gauges are already arranged in Wheatstone bridge, and all of them are active ones. So full bridge. These are in. Remember this circular zone here. All those gauges are here only, placed here. Why it is S-shaped? It is S-shaped because in S-shaped it can measure both tensile as well as compressive. If I compress it, I can measure it. If I put it like this, tensile, again I can measure it. So it is for both directions. It is S-type load cell. And finally, the last one is here with me. This is what we call the beam type load cell. So if you look closely here, you see here is one arrow. It is going in the downward direction. It means whenever you try to load it, it should be always like this, and it should bend a downward direction. In the direction of the arrow, it should go down. Then the positive result will come. If I reverse, of course it will work, but your result will be coming in the negative. So that's why they give a convention. It's just a 40 kilo capacity, and this load cell is about, not about, it's a 1,000 kilo or 1 ton capacity. So here, me and my students, we are involved in all these sort of instrumentation and activity. Now, your question time, if you have any, because time is almost up. Any question from your side, you may type it quickly. I would explain it. Oh, I have not shown you the connection wires. If you can see here, remember, look at here. In every load cell, you have this. Don't forget, this is the most important thing. The connection diagram. So red and black, these are for excitations always. White and green, these are for signal, to take the signal out. This is the input, this is the output, and finally, this is for shielding. We always use shielding in every measurement. Otherwise, lots of noise comes. So we have 5 wires, 2 for input, 2 for excitation, 2 for output, 1 for common terminal or grounding purposes to eliminate noise. Okay, any question from your side, please ask.
Guys, you can write your questions in the chat box. I think, sir, don't have any question.
Okay then. Okay, that's fine. That's fine. You can always email me. I think you might
Yes,
have my email.
yes, sir.
So just let me write down my email ID so you can
Student, later on
right.
also, if you have any
Ah,
question, you can send it to me. I will
ah, ah,
mail it to sir.
sure, sure. Anytime.
Thank you, sir, for your precious time for our GHRCE College of Engineering. Mostly you have focused on the piezoelectric strain gauge and complete bridge circuit. That is very beneficial for our students. Uh, I hope the students have enjoyed the session.
Okay, that's nice. I hope they have learned something new.
Yes, sir. And also the practical purpose, we have shown the different type of strain gauge to the students, also their arrangement. That's very beautiful. Student get to know how the research takes place from that. Thank you very much, sir.
Okay. Thank you so much. Thank
Thank
you
you.
so much.
Thank
Okay. Good day to everyone.
thank you, sir. Students, it's the end of lecture. You can leave this meeting. I will collect your attendance from the WebEx. Thank you very much.